Hello everyone, this is Mrs. Lindsay. Today we're going to talk about optimization. We're going to do this example. It's a pretty generic example, but first let's talk about what optimization means. It's really a method to find the most effective use of a resource. Typically we're talking about cost effective. And again, it finds a suitable solution. So you're really talking about kind of maximums and minimums for a problem, right? And it's within a given domain. So your problem gives you constraints that you have to work with. So let's just take this problem and see what we can come up with here. So first of all, we have the first sentence says the product of two numbers is 1,000. We don't know what those two numbers are, so we could call them x and y. We want to minimize the sum of the second number and twice the first, and we want to find the two numbers. So again, let's kind of go back to the first part here. Product of two numbers. Again, we don't know what they are, so we'll call them x and y. And we want to minimize, so I'm going to use m to stand for our minimum value there. Minimize the sum of the second number, so y plus twice the first. And that'll be our minimum value. Well, we have a system, so we can think back to our algebra. How do we actually want to go back and solve this? Get rid of a variable, so we can take our first one and we can solve that for either x or y. I'll go ahead and solve that for x, so I'll divide everything by y. And then I'm going to substitute that into my equation here for x. So I'll have m equals y plus 2 times 1,000 over y. And we can simplify that a little bit. So we'll get y plus 2,000. And then I'm going to go ahead and write y to the negative 1. Because what we want to do at this point in time is we want to use our calculus and think about minimize. Where have we minimized before? Well, if we take the derivative and we set it equal to 0, that will give us our relative and or absolute max or min. So our extrema. Okay. So if we take the derivative of our function here, so derivative of y is 1 plus the derivative here, so again power rule, so it'll be negative 2,000 y raised to the negative 2. And again, let's think about our first derivative test here. If we set that equal to 0 and we solve, that'll give us our critical numbers. So I'll subtract over a 1. And keep going here. So then divide by a negative. So that makes both of those positive. And I can also divide by 2,000. Okay. And how do we now solve this? Well, you can think about cross multiplying. A few different ways to go about working through this problem. Cross multiply, so y squared equals 2,000, and then square root both sides. So y equals plus or minus square root of 2,000. And again, let's think about that number. I can reduce that to, I know 400 goes in there 5 times, so that'd be 20 root 5 plus or minus. Okay. So let's go back and read this problem here just a little bit. Find the product of two numbers is 1,000. Minimize the sum of the second number and twice the first. We want to find the numbers. Okay. So again, these are our critical numbers right here. So we have plus or minus 20 root 5. So let's go ahead and test our critical values here. So we have our number line of negative 20 root 5 and positive 20 root 5. Okay, so I'm going to plug in a value to the right, in between, and to the left here. I'd like you to go ahead and pause and check a value. The values I was going to check were negative 50, 0, and positive 50. So go ahead and plug those into your derivative, which would be right here, and determine whether or not it's positive or negative. Okay, so hopefully you got positive, negative, positive. So again, from our first derivative test, we know that this, if it goes positive, it's going up, then down. So this is a maximum, but we are actually looking for minimum by minimize the sum. So again, this would be our minimum value right here. So our y value would be positive 20 root 5 for our minimum. And then to find our x value, we can plug that into our equation here. So we can simply, I'll use this one even, x equals 1,000 over 20 root 5. And we can reduce that. So we get that to be 50 over root 5. And then we can even rationalize the denominator. So we get that to be 10 root 5. So x equals 10 root 5. And y equals 20 root 5 is our minimum. Okay. So moving to the next slide here, I'd like you to pause the video. Go ahead and read this because these are really important. And please realize how I highlighted number 4. Determine the feasible domain. And that will come into play. The first problem that we did was very generic, but the second part, the domain, comes into play when we get to our next examples. So go ahead, pause, and read these over, and then we'll move on to our next example. Okay, so now we're going to take a look at a more real-life situation here. We're actually going to skip this problem right now. We're going to move down to the second problem on the second page. We have a rectangular field is against a barn and needs to be fenced on only 3 sides. You have 1,200 yards of fencing to use to get a field of maximum area. What should you make the dimensions of the field? So let's go ahead and draw this scenario. So if I have a barn and then I have a rectangular field against it. So here's where my barn is. And it's a rectangle, so we know that the length and the width are going to be the same. But again, we don't need fencing right here, only on 3 sides. So we have 1,200 yards of fencing, so this is regarding the perimeter. So we have 2 x's and a y for our fencing of 1,200. Okay. We want to talk about maximum area here. We want to get a maximum area. Well, area of a rectangle is x times y. So again, we want to use a little bit of our algebra here first of all. Work with our system. So I'm going to solve for y and substitute that into our area formula here. And now go ahead and distribute dx. Now we're going to use our calculus here. We're going to find our maximum area. So this is what we want to take the derivative of. So the derivative of a is equal to 1,200 minus 4x. And again, we're looking for our maximum, so we want to set that equal to 0 to find our critical numbers. And we want to go ahead and solve for that. So negative 1,200 equals negative 4x. Therefore, x would be 300. So again, let's think about our critical numbers here. 300, and we're going to test that on our first derivative line. In this case, though, we do want to restrict our domain. So clearly we're talking about a rectangular field here. So we would have to have boundaries of 0 all the way up to the amount of fencing that we have. Okay, so we want to test in between 0 and 300, and in between 300 and 1,200. So go ahead and pause. I would like you to check this, check those values, whether they're increasing or decreasing, and see if you can actually find, again, remember what we're talking about, the maximum here. So again, here we get the increasing, decreasing, and again, it cannot be below 0 because we can't have a negative amount of fencing. So we get this to be a maximum. But we want to find the dimensions of the field. So again, this is our x value, so we need to find our y. So we can easily plug that back in. I would go ahead and just plug it back into this equation. So 1200 minus 2 times 300. So our y value there is 600. So let's go ahead and answer the question. You don't necessarily have to use a fencing, but it says, what should you make the dimensions in the field? So it should be 300 feet by 600 feet. And I'll go ahead and say for maximum area. And to find that, we would use A equals x times y. So 600 times 300, that's going to give us 180,000 feet squared. And I didn't ask for that. I'll go ahead and add that in there. So again, we have some constraints regarding a real life situation there. So again, we couldn't have negative fencing, and we had a maximum. We couldn't go over the amount of fencing that we already had for our problem. Okay, so let's take a look here at our next problem. And this should be very similar to our activity that we did the other day. So we have a packing design. A television manufacturing firm needs to design an open top box with a square base. The box must hold 32 cubic inches. Find the dimensions of the box that can be built with the minimum amount of materials. Okay, so let's talk about this one here. Excuse me. So a television manufacturing firm needs to design an open box with a square base. Okay, so we know that I'm going to go ahead and just redraw this over here. I know the base is a square, so all the sides are the same. Okay, so I'm getting that right from there. However, doesn't necessarily the height say the height of the box is the same, it just says the base is a square. So the box must hold 32 cubic inches. So when you see cubic, hopefully you realize that we're talking about volume. Square inches, we're talking about area. Cubic inches, we're talking about volume. So we want to find the dimensions of the box that can be built with the minimum amount of material. Okay, so let's first talk about volume. Volume in this case of a box would be length times base times height. So x times y squared. And that would be equivalent to 32. Alright, so now we want to find the dimensions of the box that can be built with the minimum amount of material. So here we're talking about surface area. So surface area is the area of all the sides, but we want to exclude the top of the box. So we have the base, which is going to be y squared, and then we have four sides here, kind of the left, the right, the front, the back. All of those will have dimensions of x times y, and again we have four of those, so it'd be 4 times xy. Okay, so now again let's do a little bit of algebra here. We're going to take the first equation and we're going to solve it for a variable. I'm going to go ahead and solve that for x. So I'll just do it right over here. So x equals 32 over y squared. And we'll substitute that into our surface area. And we can simplify a little bit. So surface area equals y squared. So we'll have 4 times 32, which gives us 128. And then we can cancel out a y there. Okay, so before we take the derivative of this, let's clean this up a little bit so it makes our life easier by moving that y to the numerator, making y raised to the -1, and then we can take the derivative. So the derivative of the surface area, 2y minus 128y raised to the -2. Okay, so we're moving on to the second portion of the second video for day 1 notes. I would like you to, before you push play on that next one, set this equal to 0, find the critical numbers, and test the points. So once you do that, please start watching the second video.